Okay, everybody, I am back with you. This is Mr. Taylor. And we're coming up. Actually, this is the very last lesson in Unit 7. Um, and in this particular um, lesson, we want to look at 8.10D. And this is just simply uh, showing that you can model the effect of linear and area measure of dilated two-dimensional shape. So let's just get started. Again, we want to take a look at some very important definitions that we want to talk about, talking about linear measure. Um, the first definition you should be familiar with, which is parameter. And the parameter of a figure is the linear measure, and it's the distance around the outer edge of the figure. So when we look at the parameter of a figure or the parameter of a figure, we're looking at what's going around that figure. So we're looking at adding sides, adding sides, adding side lengths. The next definition we want to look at is the circumference. And again, this is a linear measurement, but it's the distance around the circle. So if we have a circle, then we want to talk about that distance around the circle. So a perimeter, and the circumference are one-dimensional linear measures. Okay, so the next thing we want to look at is positive rational number side length. So this is what we're saying. When we take the perimeter or the circumference of a particular object, we're going to have positive rational numbers. So we're not going to have a -2 or -20. All of these numbers will be positive. I think I brought that up to date when we were talking about perimeters. The area. The area is the measurement attribute that describes the number of square units a figure or a region covers. Now, the good part about this, if you're on the coordinate plane, all you got to do is count those little boxes. Other than that, if you're not on the coordinate plane, then remember the length time height. That's how you find the measure of area. Again, area is a two-dimensional square unit measure, so it's going to be something squared. And again, positive number, rational number side lengths. Positive rational number. Please understand this rational number mean it could be a fraction, could be a decimal, and of course it could be a whole number. So we are still talking about dilation. So again, let's go ahead and reiterate. A dilation is a transformation in which an image is usually enlarged or reduced, depending on the scale factor. We've talked about the scale factor, in such a way that the angles of the original figure and the dilated figure are congruent, and the sides of the original figure and the dilated figure are proportional, creating similar figures. So remember, if we got dilation, the angles are going to be congruent, and the sides are going to be proportional. So we talked about enlargements again. Let's go ahead and make sure we understand. When we have an enlargement, then we're going to have a scale factor, and that scale factor is going to be greater than 1. When we have a reduction, again, we'll have a scale factor, something that we're going to multiply by, and that particular number will be greater than 0, but less than 1. And if we are looking at a congruent figure, then the scale factor will be 1. Okay. So let's talk about the model, or should I say the model of the effect of a linear and area measurements of dilated two-dimensional figures. So dilating a two-dimensional figure by a scale factor recording the linear and area measure of that figure and image, and determining the relationship between the scale factor and the measurements. So, concept, this is what we're going to do. Okay, we want to uh, make sure that we can take this two-dimensional figure and either enlarge it or reduce it. And we're going to do that by this particular scale factor. We want to record the measure, the area, and we want to make sure that we record the 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 perimeter too of that figure and the particular image, and we want to be able to determine the relationship. So let's deal with the area part first. And if we multiply a linear dimension by a two-dimensional figure by a constant scale factor, it'll result in a proportional one-dimensional measure. We can do that also for the perimeter and the circumference. So again, multiplying linear dimensions of a two-dimensional figure by a constant scale factor result in a two-dimensional measure, which is the area that is equivalent to the original area multiplied by the scale factor squared. Now, just know this is a lot of lingo. This is a lot of jargon. These are just words. We need to see how this look in action, and this is what we're going to come to. Okay, so the first example that we have tells us that this is a parallelogram. It's not a parallelogram because these two sides are not equal, are they? Well, yes, it is a parallelogram. So we have a parallelogram, and they are A, B, C, and D, and we say it was dilated to form Q, R, S, and T. So what you know this was saying, that angle A has been dilated and became angle Q, angle B dilated to become angle R, angle C dilated to become angle S, angle D dilated to become angle T. It gives us a number here. The dimension of QRST are twice the dimension of ABCD. So if they are twice, then we must have a scale factor of 2. So in order to find the linear measurements, let's first start with the perimeter. So the perimeter will be, and let's start with ABCD, it will be side plus side plus side plus side. Side plus side plus side plus side. Okay, so this is a parallelogram. So if it's a parallelogram, we can do this thing two ways. We could say 2 times this plus 2 times this. But let's keep informed with what they're asking us. I mean, I know you guys are what can I say? You're good enough to do that. So this is 0.9 plus 1.25 plus 0.9. Please, let's not get this confused right here. This is the slant. This is the slanted height or the side, which is 0.9, and then this, of course, is 1.25. Remember, parallelogram, you have 4 sides and 2 of the sides are equal. Okay, so if we add these up, we'll get 1.25 plus 1.25 is 2.5, and 0.9 plus 0.9 is 1.8, and if we add 2.5 and 1.8, we'll get a parameter of 4.3. We also can take a look at the actual, this is the this is the image. So let's take a look at Q, R, S, and T. We have 1.8 centimeter. So apparently ST is 1.8. Then we have 2.5, and QT also must be 2.5. So we can add the image up. 2.5, again, what's the formula? Side plus side plus side plus side. So 2.5 plus 2.5 is 5. 1.8 plus 1.8 is 3.6. So 5 plus 3.6 is 8.6 centimeters. Keep these two in mind because we're going to do something with them. All right, now we want to take a look at what they're talking about as far as our area measurements. So again, the formula for area is base times height. Base is what it stands on. So let's take a look at the actual pre-image. So the base is going to be, you see there it is, 1.5. 1.5 times, now it asks us for the height, not the slanted height. So in order to find the height of this thing, then, well, actually they're telling us, we'll get to this here in about 2 or 3 days where we'll come up with how we would actually find this particular height. But here they're telling us that that height is 0.75. So this is a given, which is good for us. But we'll figure it out here shortly. So 0.75 is our height, not the slanted height, but the actual height. Okay, so if we get the height of 0.75, now we can multiply that height times the base, which is 1.25, and we'll get 0.9375 centimeters squared. Remember it said when you're dealing with measure, it'll be some unit squared. Okay, now that's the pre-image, this one. For the image, now they told us that this height, we have the 2.5 here, which is twice that. But now if they're giving us 0.75 and it says that the dimensions are twice, so that means the height of this one must be twice of 0.75, which is 1.5. And again, is area is equal base times height. We'll multiply 2.5 times 1.5 and we'll get 3.75 centimeters squared. Okay, so I know you remember this from 7th grade of how you find the area. The only thing we're doing here is we're just looking at a dilated part, which means the scale factor comes into play. So what about our relationship? How are we going to find the relationship between A and, or should I say, pre-image and image? So what we're trying to do is prove here that 2 would be the scale factor. Remember what we talked about a little earlier? We said that that formula, and I'm going to put SF for scale factor, is going to be new over original, which will be 8.6 divided by 4.3. And I'm using these figures right here. So if I divide that, I will get 2. Now, think about something for me. If the dimensions is 2 for the linear, I wonder what the dimensions will be for area. Well, we can go back and do the actual measurements, which take the area of the image divided by the area of the pre-image, and we can divide and get 4. Or we know that if we have a scale factor of 2 and the area is something squared, so then 2, you square 2, it will be 4. Now these last 2 statements at the bottom are very, very, very important for us if we understand, because there will be questions that ask you what is the effect. So if I'm looking at area of a figure, and that area will be the dimensions of this parameter, let's start with parameter, is multiplied by a scale factor of 2, or should I say twice the dimension of the pre-image, then we will have the perimeter is twice the perimeter. So you have the perimeter of QRT is twice the perimeter of ABCD. Now, what's the effect of the twice the dimension on the area? Well, if it was dilated by a scale factor of 2, then it will be 4 times the area, and that's just simply 2 squared. That's what we get for. All right, let's roll. Now, what we have here, it tells us QRST was dilated to form ABCD. So that means here is our original, and then this is our new. Or we could say this is our pre-image, and this is our image. That's what we can say. So we do the same process. Actually, it's nice if we have the same figures. So here, our original is switched places. 2.5 plus 2.5. Let me get my pointer back. 2.5 plus 1.8 plus 2.5 plus 1.8 will give us 8.6. And then, of course, our new or our image will give us 1.25 plus 0.9 plus 1.25 plus 0.9, and that'll give us 4.3. Now, the only difference here is these numbers switch, so I wonder will our scale factor switch? And I would say yes. And the reason why is because now we will have new over original, and our new is 4.3 over 8.6. Of course, we can just do some reducing, and this will be 1 over 2. So yes, we do have, and it tells us here at the bottom, the dimension of ABCD are half the dimensions of QRST, so that means that our scale factor is 1/2. Of course, going by the same process, what happens if we go and find the area? So again, 2.5 times 1.5 is going to give us 3.75 centimeters squared. This is for our pre-image or our original, and then 1.25 times 0.75 is going to give us our new. Okay, so that they switched around, but which is good. So now you see an example of a scale factor that's being dilated and the effect by enlargement, and here you're looking at a scale factor that's being dilated, that's being reduced, and the effects. So what would be the effects if we took the actual ratios here and divide? It'll give us 0.5 or 1/2. So what is that telling us? That QRT was dilated by a scale factor of 1/2 to form this one. Get back my pointer. This was dilated by a scale factor of 1/2 to form this one. And here, so we're looking at the actual new divided by the original, and that's going to give us this number divided by this number, and we'll get 0.25 or 1/4. Well, that makes sense, because if we took, and this is just math, if we took 1 over 2 and squared it, we would have 1 times 1 over 2 times 2, which would give us 1/4. All right, don't get lost here. Let's stay together. So now we will come to the circle, and realistically, the circle is not a is not any difference. We're still going to look for the diameter, and we're still going to look for the area. So the only thing we need to do here is be able to understand what the actual formulas are for finding the area of a circle and the parameter, or should I say the circumference of a circle, because that's what the perimeter would be. All right, so let's look at what we have. It says the diameter of circle D is 10 units, and the diameter of circle D prime is 6 units. Therefore, the diameter of circle D prime is 3/5 that of D. Well, how in the world did they get that? The 3/5. Well, it seems to me that D prime is the new, and that's 6, and the original is 10. So here we divide by 2 and we'll get 3/5. Or you could just say 0.6 if you choose. So let's go now and see, can we look at the linear measure and the area measure and see how will this come about. So again, for a circle, we're looking at the formula being pi times diameter. So we know we use an estimate. We're going to estimate pi is 3.14. And 3.14 times 10, and we're looking at the original first. 3.14 times 10 will give us 31.4 approximately for the circumference. Okay? Or we could say, and please make sure you look for this part too in your answer choices. Pi times diameter would be pi times 10, or 10 pi units. Either one of these would be right, but you want to make sure that you have to understand that you may see one or the other on your, as far as your answer choices. Now, for the D prime, we're looking at pi times diameter, which is 3.14, and it tells us that the diameter for this one is 6. So if we multiply 3.14 times 6, we'll get 18.84, or 6 pi units, which is this part. Just keep that in mind. So now let's go to the area part, and the only thing that you're looking, make sure that you know what these formulas are. The area formula is pi times r squared. We probably will have an area. Well, we know we'll have a formula sheet, but we should be. These are pretty simple for us to remember. So area is pi times the radius square. Now radius, how do we find the radius? Well, if we can remember from last year in 6th grade work, that radius is equal to 1/2 of the diameter, which for the first one, for D, we could say that the radius for D is 1/2 of 10, which is 5, and for D prime, the radius is 1/2 of 6, which is 3. So this is how we were able to get our radius. Okay. So now we can go to work. So finding the area of the original, we will have pi times radius square, which is 3.14 times 5 squared, right here, 5 squared. 5 times 5 is 25. Do that first, and then 25 times 3.14 will give us an area of 78.5 units squared. Units squared. Or again, if we just looked at it from the perspective of pi, we will have 5 squared times pi, or 25 pi units squared. So now taking a look at the actual image, remember 6 was our diameter, which means our radius is 3. So here we have 3.14 times 3 squared, meaning 3.14 times 9 would give us an area of 28.26 units, or 9 pi units squared. Okay, now as far as what is the relationship? So in plain words, what we're just doing here is going in and see how can we find the scale factor with this math that they have given us. So we're looking at new divided by original. So we're doing so first with the circumference. So we'll have 18.84 is the new divided by 31.4, and that's going to give us 0.6, which is equal to the same as 3 over 5. Because 6 over 10, with it being one place, that means that we definitely have a denominator of 10, and we can divide or simplify, and we'll get 3/5. So the circle D dilated by a scale factor of 3/5 to form D prime, and the circumference of the circle is 3/5 the circumference of D. Pretty straightforward, guys. Pretty straightforward. But we look at the area, we use the same process to find the relationship with the area, but of course, if we take 3/5 and square it, 3 times 3 is 9, and 5 times 5 is 25. And this is just basic math skills. If we're gonna square 3/5, then what we have is 3 over 5 quantity squared, and then that's gonna be 3 times 3. Remember, when you multiply in fraction, you multiply straight across, and 5 times 5, which will give us 9 over 25. So we could say that circle D was dilated by a scale factor of 3/5 to form circle D prime, and the area of the circle is 9/25, the area of circle D. If you can remember that whatever the scale factor is, and when we're dealing with measures, if you can remember that, guys, you can easily remember that that the area will be, or should I say the scale factor will be squared when we deal with the area. Okay? All right. So the last one is on diameter of a circle. So what I want you to do now, if you could, even though we have it here, wrap your mind around this one for me, please. Wrap your mind around it and see, can you understand how we were able, or how the author was able to go through here and get this for us. It's worked the exact same way. The only thing about it here is we have an enlargement, and it is an enlargement because it says that we have a 1.23. 1.1 and 2/3 is the same thing as 1.67. So that means, hey, it's an enlargement. So go ahead and work that for me. If you have any questions, please present them in class. And as always, this is Mr. Taylor, and guys, I'll talk to you soon. Have a great one.